Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi, I'm Sean Thompson and welcome to the fourth summary in the Padisco video series. In this one, we're going to go over probability. In particular, we'll be going over a notion of probability, formalising probability, calculating probabilities, conditional probability, and then we'll finish up with a look at Bayes' theorem. Now, so far in this video series, we've mostly been dealing with certainty. When you're given a data set and all you're being asked to do is look at it and describe it, then in principle, you can be certain about what you're doing and what you're saying. But we're about to enter a rather interesting part of statistics where the certain becomes uncertain, and that's where probability comes in. And the basic idea with probability is that it's a number that we assign to indicate the likelihood that an event will occur. But having said that, there's two major notions of probability. There's relative frequency and there's the a priori classical approach to probability. And we'll be looking at both of these in this video. To get our first notion of probability, we'll start by looking at the relative frequency approach. Now, let's just dispel a rumour. Just because a process is random, it doesn't mean that we can't study it or find any patterns in it. In fact, it's often just the opposite. Let's take rolling dice, for example. There's 6 sides to a standard die, and when you roll that die, you've got no idea which side is going to show up. It's about as random as you can get. But imagine rolling that die thousands and thousands of times. Would it shock you to discover that a 4, for example, will show up about 1 in every 6 times you roll it? Well, hopefully it wouldn't shock you, and that's why we assign a probability of 1 in 6, or 1/6, to the event that a 4 shows up whenever we roll a die. That is, we define probability in terms of the proportion of times that we see an outcome occur. This is known as the relative frequency definition of probability. And that's a very practical definition, and it's actually an empirical definition because it's based on observations we make about an event. But there's two major limitations of the relative frequency definition of probability. The first major limitation is that to get at the true probability through relative frequency, we'd theoretically like to watch the die roll infinitely many times. Obviously, in practice, we can't actually do that. And the second major limitation of the relative frequency approach to probability is that by observing an event occur a certain proportion of times, sure, we get to assign a probability, but we've got no idea why it is the probability. For example, a sociologist studying 2 schools might observe that students from one school have a higher probability of passing some standardised test than the students from the other school. These observations are great, but they don't tell the sociologist why it's true. So we're going to need to develop a more formal approach to probability. And developing this approach is what we're now going to look at. This will mainly involve formalising our definitions of outcomes and events, because when we talk about a probability, we are always talking about the probability of an outcome or an event. Now, whenever an observable procedure can occur, the different possible recordable observations are what we call the outcomes of that procedure. So flipping a coin will have 2 different outcomes. You can have heads or tails. Or rolling a die will have 6 different possible outcomes. 1, 2, 3, 4, 5 or 6. And when you list all the outcomes out like that, the list of all of the outcomes for a given procedure is known as the sample space. Now, an event within that sample space is any of those outcomes or any combination of those outcomes. So, for example, if you're going to roll a die, then an example of an event would be that you roll an even number. Now, that is actually consisted of 3 different outcomes, a 2, a 4 and a 6. So events are combinations of outcomes in a sample space. Now, with that formalisation of outcomes and events, we can define a priori classical probability. Under a priori classical probability, the probability of an event, A, is defined to be a fraction. It's equal to the number of outcomes in that event, A, divided by the total number of outcomes in the entire sample space that you're looking at. Now we'll have a look at using the a priori approach to calculate a probability. Now, this will often come down to counting. If you want to know the probability of a given event, then you have to know how many different ways that event can occur, how many different outcomes lead to it occurring. You also have to know how many different outcomes there are in the entire sample space. And one helpful tool to help us count things out is the contingency table. For example, let's say you're doing a study into the relationship between gender and unemployment. So you survey 1,000 adults and record their gender and whether or not they're employed. A contingency table could present these results as shown here. And so you can use this to count the ways events could occur. For example, you can see directly that 459 of the 1,000 people surveyed were male and employed. So the probability that a random person in the survey is male and employed is 459 divided by 1,000, which is 0.459. But by adding up various columns and rows, you can determine other things, like 926 of the 1,000 surveyed were employed. So the probability that a random person in the survey is employed is 0.926. What about the probability that a random person is male or employed? This is a fairly important example. Notice that you can't just count up all the males, there's 499 of those, and then count up all the employed people, there's 926 of those, and add them together. If you did that, you'd be counting all the people who are both male and employed. You'd be counting them twice, so you have to subtract that from your calculation. And this gives us what is called the general addition rule. To calculate the probability that A or B occur, you add together the individual probabilities, but then you have to subtract the probability that they both occur. Now, what is conditional probability? Sometimes the probability that we assign to an event will change if we're given some new condition or we're told that some other event has occurred. For example, what is the probability that an adult has children? And would that probability change if we're told that the adult in question is married? It probably would. You'd expect the probability to go up in that case, and that's conditional probability. The conditional probability of an event A, given the information that another event B has occurred, is given by this formula. We refer to that symbol as the probability of A given B. We sometimes pronounce it as the probability of A bar B. Another way of thinking about the conditional probability of A given B is it's the number of outcomes that lead to both A and B occurring divided by the number of outcomes that lead to just B occurring. Now, a decision tree is often used to help us calculate conditional probabilities. Decision trees show us the number of ways that various events can occur and how the probabilities of those events might depend on one another. Here's an example of a decision tree from the Pedisco textbook. Now, this talk is just a summary, so I won't go into detail here about how the decision tree is used to help calculate conditional probabilities. If you want to know more about decision trees and how to use them, there's a good explanation in the book. To finish this talk off, I'll go over a rather helpful tool that we have in conditional probability known as Bayes' theorem. Now, we often use Bayes' theorem when we have two events, A and B, and we want to switch their conditional probabilities around. So say you already know the conditional probability of B given A, but what you really want is the conditional probability of A given B. You want to switch them around. Well, Bayes' theorem helps you do that. Now, here we have the most common form of Bayes' theorem that you'll see. Notice that on the left we have the conditional probability of A given B. That's the one we want. And on the right, we have what is admittedly a rather complex formula, but it's actually really helpful. And to get an idea of how, let's look at an example from the Pedisco workbook. In this question, you're told that the Legal Eagle law firm is made up of 64% male lawyers and 36% female lawyers. And here are some conditional probabilities you know. You know that of the male lawyers, 44% are corporate lawyers, whereas of the female lawyers, only 24% are corporate lawyers. And what you're being asked is, if a corporate lawyer is chosen at random from the Legal Eagle law firm, what is the probability that they're male? This can actually be worked out using Bayes' theorem, which I did earlier. And if we submit our answer, the feedback shows us how to calculate that probability. Spend some time in your own Pedisco workbook to master this sort of situation. So that was probability. The key topics were a notion of probability, formalising probability, calculating probabilities, conditional probability, and Bayes' theorem.